Okay, how about we try to do some more related rate problems? Suppose I tell you that a point is moving along the curve y equal x squared so that the x dt is, I don't know, 5 centimeters per minute. And I ask you to find the y dt when x is 6. Now, what's going on? We have a graph, y equal x squared. And this point keeps moving. This point is moving along the graph. And it's just not moving any old way. There's a very specific way that this point is moving. It's moving in a way so that the x dt is 5 centimeters per second. Now, what does that mean? That means if the point is right here, just so I can graph it a little bit nicer, let's say 2 centimeters per minute. The x dt is 2 centimeters per minute. The change in x over the change in time is 2 centimeters per minute. That is, the x dt is 2 centimeters per, surprise I said minute. I'm sorry I keep changing it so much, but instead of minutes, let's say seconds. Minutes is pretty slow. Okay, so that means we're right here. 2 y-axis, x-axis. 2 seconds later, a second later, 1 second later, I go to the right 2 centimeters. 1, 2. That brings me to this point. As I only made progress, I'm moving along the graph. But with respect to x, I only went 2 over. That is, this is going to be 2. And then, a second later, I went 2 to the right. Which brings me right here, 2 centimeters to the right. And then, I went 2 centimeters to the right. Maybe it brings me down here. And then 2 to the right. And then 2 centimeters to the right. 2 centimeters to the right. 2 centimeters to the right. Well, let's see what's happening. I go 2 to the right and I go up this amount. I go the same to the right, but it seems like I just went up more than I did the first time. I go 2 to the right and I go up even more. I go 2 to the right and I go up even more. Go up this amount. I go the same 2 to the right and I go up more. Okay, the change in y is not constant. The change in y is not constant. The reason is it's not a straight line, but that's a whole other story. So it's reasonable to ask, well, how fast is it going up? Well, that's not reasonable actually to ask because I just said it's changing. It's not going up at a constant rate. But we can definitely ask how fast is it going up at a particular point. At a particular point, we can answer that question. When x is 6, put the radar gun, and when x is 6, find out how fast it's going up. Okay, so what we have is the following. We don't need this anymore. A point is moving along the curve y equals x squared. They tell us the x over dt is 2 centimeters per second. They want us to figure out what the y dt equals when x is 6. So I see x's, I see y's, I see x's, and need some kind of an equation that has y and x's. Well, there it is. Y is equal to x squared. Take the derivative with respect to t. The derivative of y is 1 dy dt. The derivative of x squared is 2x times dx dt. Now, they asked me what dy dt is, so that's good. dy dt equals this when x is 6, and dx dt is always 2 centimeters per second. 2 times 2 is 4, times 6 is 24 centimeters per second. Let me talk about why I chose to multiply 2 by 2 instead of 2 by 6. If you multiply 2 times 6, you get 12. And a lot of you may not know the 12 times table. And even if you do, the 12 times table is harder than the 4 or the 6 table. That is, you may not know what 12 times 2 is, but if you do 2 times 2, you get 4. 4 times 6, none of these numbers is very big. Everyone knows, say, up to the 10 times 10 table, up to the tens table. So, 4 times 6 lives up to that. 12 times 2 does not. Excuse me a moment. Okay, so our answer is it's going to the right because it's it's going up because it's positive 24 centimeters per second, right at that instant. Any other time, it's not going up 24 centimeters per second. Precisely when x is 6, bingo, that's how fast it's going up. Okay, let me erase my board and we'll try the next problem. So, here's a very classic problem within all calculus books. You have the water, and you have a boat in the water. Here's the boat. And then you have a dock. Here's the dock right here. And at the top of the dock, you have some kind of a pulley system. And here's somebody right here, and they are pulling in a rope that's attached to the boat right there. And what I will tell you is that this distance is say 12 feet. This distance is 12 feet. And I will say if the rope is more straight than I drew it. Let's try that again. Excuse me. There it is. So somebody's pulling in on the boat. They are pulling it in that direction at the rate of, say, 4 feet per second. Right, so now they want to know is, what is the speed of the boat when there is 13 feet of rope let out? That is, this distance is 13. What is the speed of the boat? Well, let's think very carefully and slowly. What does that mean? Well, the boat the boat is going to the left. Let's have some direction first of all. Up and down will be y, and left and right will be x. Now, we'll call that positive x. So the boat's going to the left. The speed of the boat is the change in x over the change in t. This will be the speed of the boat. Okay, so they're asking dx dt is equal to what when there is 13 feet of rope let out. Well, like I said, here's a right triangle. This is x, up and down is y, which is 12, and we'll call the hypotenuse v. So they want us to find dx dt when z is equal to 13 feet, and they told us something else. The change in z with respect to t is, well, is it 4 feet per second? Is z changing 4 feet per second? And my response is no. It's getting shorter. It's changing negative 4 feet per second. Because as you pull it in, z is getting smaller. Okay, all I said was, is I'm going in that direction 4 feet per second. But the change in z is negative. Negative 4 feet per second. All right, and now we have a right triangle. X squared plus y squared, which is 12 squared, is equal to z squared. Take the derivative of each of these terms with respect to t. Derivative of x squared is 2x. It's in terms of x with respect to t. 12 squared is a constant. It's 144. Its derivative is 0. Some of you think, oh, it has a power, so it's not 0. Well, that's not true. You have a function to a power. Keep the function the same. Bring the power down, make the new power 1 less. Do not forget to multiply by the derivative of the function. Derivative of 12 is 0. 2 times 12 times 0 is 0. The derivative of the right-hand side is 2z dz dt. Now they're asking us to solve for dx dt. They want me to solve for dx dt, or I want to solve for dx dt. So I divide by 2x, and I have dx dt. I divide the right side by 2x. The 2's cancel. You can write it as z over x dz dt. Well, for example, I know what dz dt is. It's negative 4 feet per second. And I know that we're talking about when z is 13. The question is, what's x? But this is not a big problem. Pythagoras will tell us what x is. Pythagoras just can tell me how to erase this. Okay, so we have this right triangle where we know this is 12, this is unknown, and this is 13. So we know that x squared plus 12 squared equals 13 squared. X squared plus 144 equals 169. This must be 25. 25 plus 144 is 169. So x squared is 25. That means x is plus or minus 5. But x is the length of her triangle. It's not going to be negative. It's positive 5. So I come back and I put positive 5 in. And then my final answer will be negative 13 times 4 is 52. Negative 52 over 5 feet per second. A little bit more It's negative 10.4 feet per second. And it's reasonable if the change in x is negative because it's getting shorter. Okay, that's that problem. Very classic problem. Every Calc 1 student needs to know how to do this problem. Alright, now here is another very standard problem. But first, I want to review something. I used to not understand this. And that is, I didn't understand what shadow meant. But the shadow is very clear to me now. That's the sun. Trust me. It's a perfect picture of a black sun. I say blue because I'm using a blue marker, but it comes out black. Here's the ground. Okay, right now, the sun is hitting every spot on the ground. It's hitting every spot on the ground. No shadow. But what if that were not true? So the ground is lit up nicely. Nice and shiny. It's a big red sun is shining down. But now, what if I put a tree? A tree. Now, this light beam, they used to go right, hit the ground right there, not hitting it there, because the tree is blocking it. In fact, the tree is blocking all of these beams, blocking all of these beams, blocking all of them. But once we go a little bit higher to the right, the sun is hitting this box. It's hitting there. It's hitting there. And for the record, the sun is hitting these are positions here. That is, the shadow is right here. So what you do is, you think of the sun as one point. And you connect the line between the top of the tree and the center of the sun. And it goes right here. All of this is shadow. All of that is the shadow. Okay? That's what shadow is. The area on the ground that the object, in this case our tree, is blocking. Okay, so that's what shadow means. And I'm embarrassed to say I didn't really understand what shadow meant. And as a result, I couldn't do the problem. But once I understood shadow, piece of cake. So what you have is a 6 foot tall man, just say walking. He's walking at some rate. Let's think of a good rate. Say, this should work. 5 feet per second. But because he's walking away from something. He's walking away from a, say, 15-foot light pole. Walking away from a 15-foot light pole. Okay, so I guess you can ask 2 questions here. When he is, say, 10 feet from the light pole, at what rate is his shadow moving? At what rate is his shadow moving? That's one question. Now you can maybe talk about the length of the shadow. At what rate is the length of the shadow changing? At what rate is the length of their shadow changing? Okay, so let's understand this. So instead of a sun, you have a lamp pole. So you have this 15-foot lamp pole, 15 feet. And here's the ground, and you have this man, and the man is 6 feet tall. And he's walking away from the light pole at the rate of 5 feet per second. So we'll call to the right X and up and down Y in case we need it. So with respect to the man, he's going to the right, dx dt, 5 feet per second. That's what it says. Now, when he is 10 feet from the pole, so when x is 10, right here x is 0, at what rate is his shadow moving? Now, let us understand what's going on. Maybe the man's here, and his shadow, the tip of his shadow, how fast is the tip of the shadow moving? That's what it's really asking. The tip of the shadow is right here. And then a few seconds later, the man is the same height man is right here. And the tip of his shadow is right here. And then sometime later, the man is, say, over here, and the tip of his shadow is here. So how fast is it moving? Here, what rate is, I guess we really should say that, is the tip of his shadow moving? So this is a reasonable question to ask because we drew a picture and we understand it. Alright, so now we need to come up with an equation. We need to come up with an equation. I'm going to erase a lot of this right here, and let's see what we can do. So basically, we have this scenario. This is 15. This is 6. And here's the tip of the shadow. Okay. Let this be the length of the shadow. We'll call it X. The shadow. The length. Can I actually do this problem now? Well, that's the length of shadow. Fine. That's not an incorrect statement. And here is X. This is the distance of man from the lamp pole. This is the lamp pole. And now we want to know how fast the tip of the shadow is moving. Alright, so now, let's see. We have two similar triangles. We have the big triangle, where the vertical length is 15, and the horizontal is x plus s, and this is the same proportion as the smaller triangle, which is here. The vertical distance is 6, and the horizontal distance is s. Okay. Now, we want to know how fast that point is going. Well, that distance is x plus s. So we know that x plus s is equal to 15 times s over 6. And I think 3 goes into both of these numbers 5 times and 2 times. So we know that x plus s is equal to 5s over 2. So the derivative of x plus s with respect to t is equal to 5 over 2 ds dt. Now, the question is, do we know what ds dt is? Okay, here's how you can do this problem. Here's how you can do this. Take away s from both sides. Take away s from both sides. The left-hand side is x, and the right-hand side is 3 over 2s. So, the x dt is equal to 3 over 2 times ds dt. And we know what dx dt is. It's 5 feet per second. And this is 3 over 2 ds dt. Put the 2 on top. Put the 3 on the bottom. We get 10 over 3 feet per second is equal to ds dt. And to be honest, I'm fed up with this problem. I'm not going to do the other part. I'm not being very clear about it. I'm sorry. Okay, now, let's try one more. Yeah, actually, that's it. Okay, good luck with these problems. Thank you.